now.
Sorry, I had some issues with the tablet. Last lecture, we started to talk about the direct kinematic for a manipulator. And to start to talk about that, we were introducing homogeneous transforms. Some of you were asking me about the SCARA robot example that I was giving you. A SCARA robot, in this case, we are considering just the first 3 degrees of freedom. So think about a revolute shoulder and a revolute elbow and a prismatic joint. And 2 of the revolute joints have parallel axes. And we can, a real SCARA robot has also an additional revolute joint at the end effector. So let's say we have a 4 degrees of freedom robot, or 3 in this in the slide, and I want to compute 6 variables because I want to set compute the orientation corresponding to some joint configuration and the position of the end effector. And inside this mapping, 2 out of these 6 variables will be fixed. So it's perfectly possible to always compute the 4 kinematics, even in the case the number of joints is smaller than the dimension of the task M. But what I cannot do is the other way around, so the inverse kinematics. That means I cannot arbitrarily, given 6 arbitrary number for position and orientation, I cannot realize these numbers placing the robot in a certain configuration using only 4 joints, because we cannot cover a 6D space with a 4D one. That was the thing. And another recap from the last lecture, we described different ways to represent orientations. In addition to the rotation matrix that usually always have no problem with singularities, we introduced the angle axis that we remember is a non-minimal representation with 4 parameters. Its advantage is to use it for interpolations, and the angle axis has the peculiarity to have 2 solutions in a correspondence to certain orientations, and also have singularities in correspondence of an angle equal to 0 or plus minus pi. And this is because the axis, the rotation axis, is undefined in that configuration. So if we want to say what is a singularity, we can say that we have a singularity when there is many-to-one correspondence between the representation and the orientation, or when there are discontinuous jumps. So if you want to, let's say, have a continuous trajectory for the orientation, and you have singularities in the representation that you choose to represent your orientations, in your representation numbers, you can get very big motions or changes or jumps, or you can have multiple solutions. And this is, of course, a problem if you want to control the orientation through closing the loop on the representation that you choose. I need to underline that the exponential map is not really the representation of orientation. It's just the rotation vector, so the 3D vector that is the representation of the orientation, and the exponential map is just the way you map into rotation matrix. See, this was a clarification that I had to do. Yes.
I think the slides on the whiteboard are stuff. Not sure.
No, I'm just doing a recap now.
Okay.
Yeah. Then we also talk about Euler angles. that is a minimal representation because they have 3 parameters. They also have 2 solutions of the inverse problem. So 2 set of Euler angles corresponds to the same orientation, and they also suffer for singularity in the situation, for example, where you have the gimbal lock problem, where you have 2 axes aligned in the yaw and roll axis, for example. Finally, we discuss about the also the quaternions. That is a non-minimal representation because it has 4 parameters. They have the advantage to don't have singularity, but on the other way around, they have the problem of having need a constraint of having a unit norm on them, and they also need a spatial algebra to do computation. For example, like composing rotations. Now, if we go back to the point where we left, we started to introduce homogeneous transforms that are 4x4 matrix that allows to encode roto translations, and they are linear operators. And the advantage to have these transforms is that we can concatenate as we did for a rotation matrix. So this is where we left. It's a concatenation, a composition of 2 homogeneous transforms. One that maps, describe the orientation of frame B with respect to frame A. This time, these frames don't have the same origin, so they have different origins. That's why we talk about roto translations. And the other orientation is from the frame B to the frame C. And if we compose these rotations, the roto translations, we see that we can have a third transformation that is from the frame A to the frame C. Okay. And this is a generalization of what we did for rotation, but with frames that have different origins. So they involve roto translations, and the important thing is that these transformations do not commute. So the order matters, as in the case of rotations. Now, what about the inverse of a homogeneous transform? We can always derive an inverse of homogeneous transforms. It always exists, and it's the same thing as swapping the frame A and B as we did for the orientations, for the rotation matrix. So yes, let's say this is the transformation between that maps point from the B frame to the A frame. So this is a point on the A frame. This is the point on the B frame. We need to rotate it from the B to the A frame plus sum the vector that is between the origins of the 2 frames expressed in the A frame. And this corresponds to this transformation. That we remember will have a 1 in here. It's a 4x4 matrix. While now we consider the TBA, which is what we said is the inverse, and this will be composed with a rotation matrix BRA with the difference between the two origins from origin of frame B to origin of frame A, this vector expressed in frame B, and a 1. And this is equivalent to this. That maps a vector in frame A into a vector in frame B. If we want to use, in essence, this data to compute an explicit expression for the inverse, we try to do the following. So we have PB, and we try to work out, use this PAB in A, and we know that we need to put a minus because the vector from origin of frame B to frame A is the same as the minus the vector from origin of frame B to frame A. And we also need to consider the rotation to frame B. So this is the same as this. Then we need to do something more. Well, for now we copy this. But we want to use also this data. So instead of using BRA, we use RAB transpose, its inverse, plus we do the same here. And this corresponds to the transformation ARB transpose minus ARB transpose Okay. So starting from the data that compose T8B, ATB, we can compute its inverse. So we have a formula to compute the inverse of a homogeneous transform. And we can check this is an inverse by pre or post multiplying by ATB and see that we get this, which is the identity matrix, is an homogeneous transform that is represent no rotation, no translation, that has the identity matrix here, a 1 here, and zeros in these locations. And as I said, this is a explicit expression for the inverse. Now, let me introduce two basic transformations, one for the pure rotation and one for the pure translations. How does it look like the homogeneous transform for a pure rotation? So what, let's say we call TR and a 0 here. In your opinion?
We have the rotation matrix on the top right, top left corner.
Top left, yes.
Then on the top right, we have zeros.
A column of zeros, yeah. Okay.
One on the bottom right.
A row, right? So we do 0 transpose. Let's say we assume that 0, this is a column vector. Okay, very good. And for the translation part, let's see, this is a translation between origins. What do you get?
Now identity matrix.
Okay, yeah, because we don't have rotation.
Then the translation on the right, and the same on the bottom.
Okay, very good. So we have these two basic transformation in these two cases. Now we can try to do an exercise. You will find it also in MATLAB, this exercise. The exercise is the following. Consider like a block with a frame that initially is aligned with a frame A, and we apply the following transformations in the given order. First, we translate this block along the x-axis by 3 meters. Then we do a rotation again about the x-axis by 30 degrees. And then we do a translation around the new y-axis by 2 meters. And we want to compute the homogeneous coordinate of point P on the block, which is on this corner of the block. And it's 1 meter, 4 meter this dimension, and 2 meter this other dimension. So how do we proceed? First, we do the drawing. I think it's useful to understand. And we see the original frame A is here. Then we move along this X direction with a translation. So the frame B, which will be the resulting from the first transformation, is aligned with the frame A because we are considering only a pure translation. Then we do a pure rotation about the XB axis, and we obtain the frame C. That will be 30-degree rotation. Then again, we do a pure translation along this axis and of 2 meters, and we get the D frame. And once we have the D frame, we know that the block is this one and is located in the D frame in this way. So once we have the D frame, the point P in the D frame, it's how much? X-axis. So we said from the x-axis, on the x-axis, we have a 2 meter component. Then we have on the y-axis, we have 4 and -1 on the z component. Okay. Then to compute the homogeneous transforms that represent the position orientation of point P in the original frame, in the frame A, we need to compute all the roto translations. So first, we can start to compute the homogeneous transforms from frame A to frame B. And how does it look like? This is a pure translations. You just said, we just saw it a few seconds ago.
Well, we have the identity matrix, and then should be 3 millimeters, 0 and 0.
Okay, 3. So the translation vector is
3, 0, 0.
3, 0, 0. Okay, very good. And a 1. Very good. Okay. Then we need the transformation between what? Frame B and frame C. And this one we said is a pure rotation by 30 degrees about the x-axis. Pure rotation means that we don't have any translation. So we can already fill in what? Fill in that the translation part with 0, 0, 0. Okay. What about the rotational part? You remember the elementary rotation about the x-axis? It had 1, 0, 0 here, then 0 cosine of 30 degree, sine of 30 degree, 0 minus sine of 30 degree, cosine of 30 degree. And again, you have zeros underneath. Okay. Finally, what we miss? We miss the final translation. That is a pure translation between frame C and frame D. And is a translation along the YC axis. Of how much? Of 2 meters. So how does it look like? We said it's a pure translation. So identity matrix for the rotational part, we have again zeros. And for the transitional part, we need to express this vector between frame C origin and frame D origin. And this vector is where? Along the Y axis of frame C and as a component of 2 meters. So along the Y axis, something like this. Okay. Then we pack everything together. We compose all this transformation, the one from frame A to B, from frame B to C, and from frame C to D. And we know that this is the transformation we are looking for that maps. Remember, the two interpretations represent frame D with respect to frame A, or maps vectors from frame D to frame A. So it's also a change of coordinates, the same as rotation matrix. And we will see the value will be, if you try MATLAB with this data, there is an exercise, you will get these values. Okay. Okay, everything I hope is clear. Then what about frame placement? So we said that we can attach one frame to each link, but the only thing is, we said until now that they need to be just rigidly attached to the links. But is there a convenient way to select these frames? Is there a better way to do that? And the answer is yes and no. An old school way that people used to teach is using the Navier-Tarterberg convention. This is a systematic way to define the link frames that requires only 4 parameters to locate the frame. And the advantage of this is that allows for faster computation of the kinematics, but the big disadvantage is that you cannot choose any placement. And nowadays we no longer use that. So I decided not to teach this, because we today we use the URDF model of the robot. So you a description of the kinematic tree that allows the user to select a generic frame placement. But we will see that there are some recommendations to follow that most people follow, and we will see what are the ones. One convention is the numbering of joint and links. We see that we start from the base link with number 0, then we have a first joint, then a link 1, and then a joint 2. And we have a go up to the joint n that support the last link, last body. And then we have the end effector. And usually the end effector is defined as a rigid transform with respect to the last link. And we said we are not considering spherical joints or 2 degrees of freedom joints, so each joint has one axis, and they can be either revolute or prismatic. This is an example of prismatic, and these ones are all revolute. And they have these signs to recognize them. Now, I show you here a generic section of the kinematic tree of this of a generic robot that shows 2 subsequent links connected by a revolute joint. And we see here that the recommendation is to place the link I frame, like this is the link I, and this is the link I frame, such that as the origin coincident with the supporting joint, which is joint frame I. So this is joint I. That supports link I. The x-axis of the link frame is usually along the main link dimension. So if you have a longer link, you select the x-axis this way. And about the joint I frame, usually we set the z-axis as the of the frame as the rotational axis in case of revolute joints, or in the prismatic direction the joint moves in the case of prismatic joints. And the pose of the I frame, joint I frame is specified in the URDF model as a rigid transform with respect to the supporting predecessor link. So you need to think about a chain of transforms that goes from link, then to the joint, then apply the joint rotation, then again another roto translation rigid one to get the next joint and apply the joint again. And we can find all the frames along the structure for all the joints and links. And as generalized coordinate, you remember we discussed about that. We consider the angle between the of the joint, the angle in case of a revolute joint, the angle between the 2 xi axis of the following and preceding link. And in the case of prismatic joint, the distance between these xi axis and xi minus 1 xi axis. Okay. Everything is clear? Okay. Okay. So now that we have placed our links, frame links and joint link frames in along the structure, we can compose the all the transformation from base to the end effector and obtain the direct kinematics for a serial manipulator chain. And this, if we write it down, is we have the end effector frame and we want to compute the transformation between the base and the end effector. I don't understand why I cannot write. This will be the transformation between the base, sorry, this is a typo, and the first frame. And so the first link frame, and this transformation will depend only the Q1 variable. So the variable of the first joint, because we said that there is a rigid transformation between the joint frame and the link frame. Then we have transformation between frame 1 and 2. It will depend only the second, and so on. Till we get to the n-1 transformation between the n-1 frame and the n-link frame. And finally, we said we have another rigid transformation that doesn't depend on a joint variable between the n-link and the end effector frame, which is this one. Okay? And this is a rigid transform. So the important thing is that each elementary transformation is a direct function only of the correspondent joint that drives the link, and we can consider the once we compose all this rotation, we can inspect the homogeneous transforms, and we recognize that we can extract, for example, if you're interested only in the orientation, we can extract the rotation matrix between base and end effector, also the end effector position in the base frame. And if we want to express the direct kinematics in this way, so we, for example, we want to select, have a vector with position of the end effector and a set of Euler angles that represent orientation, then we directly copy this from that and we do a mapping to Euler angles from the rotation matrix. And we get our task variables, for example, in case of position orientation of the end effector. And this is the alternative form of the direct kinematics seen as a nonlinear operator. Now, in case of if we want to do an example, we can consider, for example, a 3 degrees of freedom planar robot, which is could be a typical manipulator structure in industrial robots for pick and place operations. And in this case, we can compute the direct kinematics based on some geometric intuition. First, don't think about that is a requirement that the links are parallelepiped or strike line are isotropic and like very regular. They could have whatever shape you want. For example, there is a robot, a quadruped robot con animal that has lower legs that are C-shaped, so they are curved. The important thing is that you need to know that whatever shape you have, you can always find the skeleton sketch, which is a representation of a kinematics of the robot that allows you to do the kinematic computation. And in essence, you need to consider the axes of the joints and you connect them with lines. And we saw that we can, what we usually do, we choose as generalized coordinate the relative way. So this will be the first generalized coordinate. This will be the second one that is defined with respect to the line of the first previous link. And the third one will be this one. So if we consider when we place the links, we start from the base frame, which is the first one. So we want to place the frames. We place the base frame, which is the first one. Then we have the length of the first link, the first joint coordinate, and then we have the second frame aligned with the this is the sorry, it's a frame of the joint that is with respect to the previous link, and then you have the next ones till the end effector. The task here is to define a position and orientation of the end effector. So in this case, since we are in the plane, we still consider as a 6D task. So you will see whatever we saw a similar situation with the SCARA robot, that we have a 3 degrees of freedom robot and a 6 degrees of freedom task. And the 3 degrees of freedom will be the set of the angular position of the 3 joints that are packed in the vector of generalized coordinates, Q, that we call Q. Now, if we want to, first we do some observations. In this particular case, we see the first observation is that the revolute joint axes are parallel. The second observation is that the links all lie on a plane x0, y0. And the third one is that the axis xi are along the link directions. Well, this is not, we said this is the frame axis. Okay, yes, forget about this. Anyway, this is a recommendation to locate the x-axis along the link main direction. And what we want to write here is the forward kinematics. So for example, the position and orientation of the end effector. And we can see that in this peculiar case, we can directly compute it by intuition. So this is the position of the factor, let's say, of this point in the base frame, in the zero frame. And we can see that if we want to compute the first, let's start with the z coordinate. Since we are in the plane, we don't have any z coordinate change. So there will be a 0 here. And then about the x coordinate, we need to consider this segment. And we see that this segment is composed by the first link, cosine, the first joint, so this segment, then the second link, cosine this angle, that is what? The sum of the first and the second joint angle plus the third link length times an angle that is theta 1 plus theta 2 plus theta 3. So the cosine of the sum of the three angles. And the same for the sine. For the y coordinate, we get this segment. So we want to get this, sorry, this coordinate. And we get the first segment here plus this segment here plus this segment here, that is a3 sine of 1, 2, 3. And we see here that this variable is not a function of q. So the same as in the scalar robot, we could not, we had a fixed orientation for some orientation direction. Here we have a fixed z coordinate that we cannot change with our joints. Then the orientation, how does it, the frame 3 is oriented with respect to the frame 0? You know about that. How is it oriented? Which kind of orientation rotates? Which kind of rotation rotates frame 0 into frame 3? What? A rotation around the z. A rotation around the z-axis of how much? The sum of the three angles. The sum of the three angles. Very good. So we have theta 1, theta 2, and theta 3. And this, we remember that is cosine of is a 0, 0, 1 in the z-axis. It's a cosine of theta 1 plus theta 2 plus theta 3. I just use this simple notation for simplicity, and minus sine of theta 1, theta 2, theta 3, and a cosine of theta 1, theta 2, theta 3. Okay. So we computed the direct kinematics. We can even compose now the homogeneous transforms if we want to use this later to do other computation. Okay, this P is we should do 0, 3. Should call it the vector between the 0, the origin of the base frame 0 up to the origin of the frame 3. Okay, then we can do the last exercise, and this time we don't use the geometric intuition because the robot is more complex. It's a RPR. This is an R. So two revolute joints, this one, and one prismatic one. And in this case, let's have a look to the transformation, the homogeneous transforms. But before looking at the homogeneous transforms, we need to see the frame placement. I already drawn that, so we just verify what we did. We have two revolute joints. So the Z axis for the base frame will be coming out from the page, from the zero frame, and coming out from the page also for the third one. And then we have a prismatic joint, and this will have the Z-axis along the joint motion, linear motion. And the distance between these, the x-axis, x2 and x1, is d2, is the linear motion of the joint. So whenever there is zero motion of the joint in a let's say we want to consider like the zero reference, we have that the x2 vector it's aligned with the x1 vector. And so if we want to compute the homogeneous transforms between the links, we start with the first one between 0 and 1, and we see that the first transformation is doing what? So this one is the first link. There is a joint in the middle, and the joint performs a rotation about the z-axis. So we have a pure rotation around z0. And no translation. So we set a set of zeros in the translation part, and in the rotation, we put the rotation about the z-axis, which is, we consider the first θ1 joint angular position. So the cosine of 1, sine of 1, 0, and minus sine of 1, cosine of 1, 0. Okay. Then, what about the second one? This is trickier. So transformation between joint, frame 1 to frame 2. We have a rigid transformation and a joint, prismatic joint in the middle. And the rigid, first we need to shift of a fixed distance A2. So from here, we need to move here. And then we need to translate of D2 along this direction. And we see, if you look at the axis, we see that the axes are not the same. So to do so, I will first consider the rigid motion of the axis, rigid transformation, sorry, of the axis, and then we will add the translational part. So if we look at the rotational part, we see that the x3 axis, sorry, x2 axis is the same as the x1 axis. Okay, and therefore we have one here, which is the dot product with respect to the x1, you remember, and a 0 in the other two directions. Then I noticed that the y2 axis, it's pointing So like this is pointing out from the plane and is aligned with the Z1 axis that is also pointing out from the paper. And finally, I look at the Z2 axis and I see that is opposite to the Y1. So to build the rotation matrix, in this case, I simply look at the Y2 axis here and I say this is like the Z1 axis. So I put one in for its projection along the Z1 axis and 0 for the other one, while for the Z2 axis, which is the third column, I project along the Y axis with a minus, and I have zeros here. Then we apply the joint transformation, which is a prismatic joint, and this prismatic joint will do what? Will move. First, we move rigidly along the x1 coordinates of how much of h2 as a translation, and we apply then the joint motion along the y1 coordinate. And we move, since the convention is to be positive in this direction, and the y-axis in the other opposite direction, we put a minus d2. And on the z1 axis, we don't have any motion. So this will be the homogeneous transform. And finally, we need to do the last step, that is finding the transformation between the frame 2 and frame 3. As before, let's consider first the rigid transformation. We set the third joint variable to 0. This means we are aligning the x-axis together, x2 and x3. And if we look at the previous drawing, you get something like this. And if you look at the frame 2 and the frame 3, you see that in essence, you can obtain frame 3 by rotating frame 2 minus 90 degrees about x2 axis. So we consider this first rotation of minus 90 degrees about x2. And this is, how does it look like? So x2 axis will remains the same. Then we have what? So we have y3 axis, you use the right-hand rule. It's opposite to z2. And z3 axis, it's the same as y2. Then we apply the rotation due to the joint. So this is the theta 3. Sorry, this is theta 3 to avoid confusion. And this rotation is around the z3 axis. So again, we have the usual rotation, elementary rotation. about the z-axis. Finally, to compute the total composition of the two rotation, which is the one that we need to map to represent frame free orientation with respect to frame 2, it's composition of what? Of the rigid one times the joint one. And this will be, if you do the computation with MATLAB, should be something like that. Then we know that there is no translation, and we get the homogeneous transform like putting this rotation matrix, no translation, and finally, if you want to compute the total transformation between frame 0 and frame 3, we obtain this.
Excuse me.
Yes.
Excuse. Can you come back to the previous slide?
Yes.
The previous again. Yes, in here. But we do the rotation and then the translation. Shouldn't it be D2 on Z and 0 for the translation, A2 on X, 0 on Y, and D2 on Z? Because we
why?
Because we do the translation, the rotation, and then and so we got the reference frame, the violet reference frame, and then we do the translation.
Yeah, but here we are doing two things, everything in the frame 1. So I agree that I said that, so we skip the joint frame, the fact that we have a joint frame acting aligned with the prismatic joint. We consider just the motion of the prismatic joint will be on the y coordinate. I agree. We try to do one step in one step this, while in the next one we split. So yes,
Okay. No, maybe I was wrong.
Very good observation. Yes. Yeah.
Okay.
So you always think the frame where you want to express these columns and this position vector. So in this case we are considering frame 1, but I agree we should have considered the if you want to apply the orientation about the z-axis, and the z-axis is not aligned with the original frame, then you need to consider this translation, this additional rotation. Yeah. So if we put everything together, we get the transformation between 0 and frame 0 and frame 3, and we can recognize that we have some simplification to do here. So here we have we can recognize the trigonometric relationship for addition and subtraction, and in this case we have cosine of 1 cosine of 3 plus cosine of 1 sine of 3 is in essence this one, and it's the sine of 1 plus 3. So with a minus, again, it becomes this term. Then we have here cosine of 1, cosine of 3, minus sine of 1, sine of 3. And we have this case, so it's cosine of 1 plus 3. And the other one are similar. So what is again useful to observe is that this is again an elementary rotation about the z-axis. So if we look at our drawing, we can see that was the case, because if you look at the frame 3, these are the x1 coordinate, y1 coordinate, sorry, frame 0 is like this, and frame 3 is just rotated about the z-axis. And while for the translational part, if you look at this vector, it's just the position of the end of the frame 3 origin, that now we consider the end effector, but it's a frame 3 origin in frame 0, in the base frame, because you can work out the x, y, and coordinate, and you will see that they are looks like this. So whatever we computed makes sense also in terms of intuition. And as an exercise, you can do this computed kinematics for a cylindrical manipulator at home. And the final remark is that the direct kinematics allows us to define the reachable workspace of the end effector. So the set of points that we can position the end effector given the joint allowable configuration. So the workspace of the end effector will depend on kinematics, but also on the joint limits. So if our joints cannot move completely, these limits will also shape the boundary of the workspace of our robot. So this, I will do the break now, if you have any question before. Okay, let's. And so as inputs for inverse kinematics, we can have the what we saw, that is the homogeneous transform between base frame and effector, or last link frame, and or whatever set of task variable where, for example, we said that for kinematics could be defined for whatever point, like the position of the elbow, for example, or just the position of the end effector and not the orientation. So we can be generic. And the equation that we need to solve to compute this joint position are typically nonlinear. And in general, there are m equation in n variables. So the question we need to answer is first, if a solution exists, and this is strictly related to the definition of the workspace. For example, if the point that we are asking to compute the inverse kinematics is out of the workspace, then in this case, there is no solution. When a solution exists, the second question is if it is unique or exist multiple solutions. For example, multiple joint configuration correspond to the same pose. And whenever this solution exists, how can I compute them? And if I can compute them in closed form, or I need to resort to some numerical approach. So this is the block diagram of inverse kinematics block. And in this case, for example, we see an example of the KUKA robot with 6 degrees of freedom. We in general KUKA robot has 7 degrees of freedom, but in this case we are considering only 6, where we have we want to compute the inverse kinematics of a certain pose that correspond to a certain position of the end effector and orientation. In this case, expressed with the Euler angles. And the solving inverse kinematics, we see that we get a set of angular position that correspond to this pose of the end effector. And in general, if we would like to solve this problem analytically, which means we want to write solution that are function of the data of this data here, that computes out in a single shot the set of joint position. In general, there are some, because we have the solutions are not unique. We have multiple configurations corresponding to the same pose. We need to deal with this in the code. So in our inverse kinematic code, we need to consider option with if then else constructs in order to get one solution or the other. And in this case, this is the same we did for Euler angles. We saw there are 2 solutions. In this case, the solution will not differ between each other by a plus or a minus, but can be very different. There are some numbers. Then about the question of solvability and existence of the solution. A solution exists if it's inside the reachable workspace, and then we can define the reachable workspace as the set of position of the end effector that can be reached at least with one orientation. So if the sorry, this is the R. If the end effector doesn't belong to the reachable workspace, or that we call primary workspace as well, VS1, then there is no solution to the inverse kinematics. If it belongs to the workspace, to the reachable workspace, then it means that there exists a solution, but that I cannot realize any orientation. And what does it mean, this? We will see in another example. Roboticists also define another workspace that is a subset of the reachable one, and is called the desk throws workspace. And in this case, it's a set of position of the end effector that instead can be realized with any orientation. And any orientation among the ones that we can that are feasible. For example, if you are considering a planar robot, the only feasible orientation is the one, the dead axis. It's about the dead axis. It's not possible to achieve other orientation. So these are the feasible orientation. They will depend on the nature of the robot. The same for scalar robot. Not all the orientation are possible. And in this case, a solution for the inverse kinematics exists for any orientation. This is an example of a Fanuc robot of the workspace for a Fanuc robot that you can find in a datasheet. So in this case, you fix the first joint, and you can move the other 2 joints and see. for example, this area that represent the reachable workspace, and if you do a view on the from this side, you can see that the workspace for the it's the whole sphere, because you can move the joint Q1 along all the circle. And then if you add a spherical wrist to the 3 degrees of freedom robot, then that can move with whatever without joint limits, then you can achieve whatever orientation. So you have that the primary workspace, the reachable workspace, is the same as the dexterous one. But let's go back to our old friend, the planar 2 degrees of freedom arm. And let's assume we don't have any limit in the joints. And to compute a reachable workspace, I consider, for example, the circle that you generate whenever the arm is completely stretched. And you see that in this case, you can only have one orientation possible, because that depends on the position of the two joints. And you can completely fold it, and in the case that the link lengths are different from each other, you cannot, in essence, place the end effector inside this circle. In a case, again, in this case, you have only one orientation possible in the plane. While for all the other point in the middle, like for example, all this in the blue area, you can have two orientations. And so to define the workspace, the reachable workspace mathematically, with an analytic expression, these are the set of the points in the 2D plane for which the norm is inside the the absolute value of the difference of the link lengths and of the sum of the link lengths. In this case, if we want to consider the dexterous workspace for which all the orientations should be possible, we see that it's completely empty, because in the middle point we said we have two orientation possible, and in the other point only one. In the case of equal lengths, we have that this becomes 0 and this becomes 2a. So this is the situation, and we have a complete the workspace is VS1. It's a full circle. And in the case of equal lengths, we know that if you completely fold the end effector, we can put it if you completely fold the arm, we can put it in the origin, and the origin can be achieved with any possible orientation. So the dexterous workspace is contains the origin point. Now, let's consider about an anthropomorphic manipulator with 3 rotational joints. And And for now, consider just the task of positioning the end effector without considering the orientation. So I want to position the end effector here. And in this case, we have 4 solutions for the inverse kinematics. Why 4? Because we do have 2 solutions that are called the elbow up solution, that is this one, and the elbow down solution that will correspond to the same end effector position. And plus we can have the solution if we put the shoulder joint facing with the robot facing the point or not facing it. So think about 180 degrees rotation of the shoulder joint, and this will still correspond to the same end effector position. So we have 4 solutions for the inverse kinematics for all these combinations. And if we add a spherical wrist, you remember, so we have a 6 revolute joint robot where the spherical wrist are 3 revolute joints added at the end effector that have intersecting axes. The fact that we have intersecting axes allows us to we can see these 3 joints as a sequence of Euler angles, because the let's say the 4th joint Q4, it's a planar rotation. Then there is the following one that is a planar rotation after the first rotation, and the 3rd one again after the first 2 rotations. So we can see these Euler angles, this joint as a set of Euler angles to represent the orientation. And we know that for Euler angles, we have 2 solutions to represent the same orientation. Therefore, in total, combining the 4 inverse kinematic solution in the previous case, we multiply by 2, we can get 8 solutions. In this case, we see the elbow up solution right, the elbow down solution right, elbow up solution left, elbow down solution right, that are appended with the 2 solution for the last 3 joints of the wrist that result in the same orientation. Okay. Then let's summarize. So we saw that in case of a planar 2 revolute joint arm, we have 2 regular solution, and in the whenever the end effector is in the reachable workspace, and 1 solution whenever it's on the boundary of the workspace, either inner or outer. But we can avoid this in code by, for example, avoiding the complete arm extension or the complete folding. In the case of 3 revolute joint arms, we have 4 regular solutions most of the time, and in the reachable workspace, and 2 solutions whenever we are on the boundary, because whenever the let's say the 2D part it's completely extended, we still have the possibility to have the shoulder joint facing or giving the back to the point. And an interesting point is that in this example, we consider an offset of the second joint with respect to the first one. So the 2 axes are not are intersecting, but in essence, the plane is not of the next joint. Octavio?
Yes. Yeah, we lost connection. I mean, I think you lost connection there.
Yeah, now I'm back. Okay, in this situation, for example, we have...
You're not sharing the screen yet, I think.
Okay.
Okay, now we can see them.
Okay, in this situation, I was saying that if you don't have this offset, then you can have the arm on top of the to have the end effector on top of the axis of the base shoulder joint, and in this case we have infinite solution because you can rotate the base shoulder joint as you want and still correspond to the same position of the end effector. So to summarize, if you have n degrees of freedom and the task dimension that is m, and we don't consider these singular solutions that I was, for example, the one on top of the base joint axis, it's a singular configuration. We consider only the regular ones. Whenever n is lower or equal than m, we have multiple discrete solutions, while whenever we have n bigger than m, we say that the robot is redundant for the kinematic task. So we define the task, for example, position of the end effector or position of the point of the robot, and if the dimension of the degrees of freedom is bigger than m, then we have a redundant robot for that task. And in this case, the regular solution are infinite to the power of n minus m. And we can see here in this video, where we have a Dexter arm robot with 8 revolute joints, and we see that self-motion, we are assigning a task dimension of 6 to keep the end effector position and orientation fixed, and we can see that the robot can still move all the joints, keeping the end effector fixed and the orientation fixed. This means that we are assigning a task of dimension 6, but we have 8 joints, so we have infinite to the power of 2 configuration to realize it. The question 3 is, can I write these solutions in closed form? And the answer is yes, but only in some special cases. These cases require geometric intuition, usually, and always require an expression of the direct kinematics. So to find an example, we can consider again the planar 2R arm. And first, we compute the forward kinematics analytically. And in this case, we have the position of the end effector that, following the procedure that we described before, it computes the x component of the end effector, multiplying the link length times the cosine of the first angle. So this vector plus the other part, that is the length of the second link, times the sum of the first and the second angle, the cosine of the sum of the first and the second angle, and the same for the y component. Okay, now what our intuition tell us? We have input data, which is our end effector position, and we want to find Q1 and Q2 for to solve our inverse kinematics. And we want to, what we can do, for example, we can try to square and sum these two equations, because we know that the distance of the point P with respect to the frame origin O, it's dependent only on the joint Q2. Think about that. You can, this distance, it's only dependent on this angle, because the Q1 angle will just rotate the point P around. So to compute the distance, for example, I compute the square of the Px component plus the Py component, and this is distance squared. And we see here that we get one term, L1 squared times cosine of theta 1 squared plus L2 squared cosine of theta 1 plus theta 2 squared, and the same for the sine. Plus, we have the double product of these two. And if we look at this, we can see that we can collect these two, and we have, in essence, L1 squared, because cosine 1 squared plus sine 1 squared it's 1. And if we collect the other two, we have L2 squared. When we put these two terms on the left, first let's apply again the trigonometric formula we know. And this is cosine of theta 1 plus theta 2 minus theta 1. That remains, in essence, cosine of theta 2. Then we can isolate theta 2, because now nothing depends anymore on theta 1. So on Q1, sorry. We can put these ones on the left side, subtract them, and divide by this term that is always positive. And again, we get an expression for the cosine. So here we resist to the temptation to, in essence, compute the arc cosine, and we do the usual trick to use the tan2 function. So first we compute the sine and doing the square root of 1 minus cosine, and we get two solutions. And this solution will be exactly the corresponding to the elbow down and elbow up configuration. And then we compute the value of joint Q2, doing the arctangent, the tan2, sorry, of the sine and cosine. Because the arccosine is defined only in 2 quadrants, and while the tan2 is defined in the 4 quadrants. And the cool thing is that when we compute the cosine of theta 2, we know that we have a value between -1 and 1. And if we put the expression of cosine of theta 2 between -1 and 1, we can see that in essence if we consider the inequality, putting this on the right side, we see that in essence, this inequality is the same as requiring that the position of the end effector is inside the outer line of the workspace, while the other inequality with -1, if you put that on the left, you can see that is requiring that the point is out of this circle. So in essence, for free, you have a check that the end effector is inside your primary workspace. Then we can use a second intuition, for example, for the computation of Q1 variable. We can consider the Q1 as the difference of two angles, which is one is alpha angle minus beta. And in this case, we compute with the atan2 function. We consider the alpha angle. We apply the atan2 to the y component py and the x component px of the end effector, and we get the angle solving the arctangent. While for the b, we consider this triangle for the beta, sorry, and we see that the sine component is L2 sine of theta 2 of Q2, and is this one, while the cosine part is L1 plus L2 cosine of theta 2, which is this one. And we need to take care in the code that this is the difference of these two atan2 is inside the minus pi and pi, so we need to do some remapping. But that's the trick. So we found a way to compute the inverse kinematics. We are almost done. We remember that oh my God, PowerPoint crashes. Where you can find this example. I think I implemented a more complex one for a 3 degrees of freedom Revolut joint robot. So you can play around setting different values for the end effector and see there is a plotting feature that plots the shape of the robot in correspondence of each end effector, and you can check the computation. You need to, in essence, use the same idea that we did for the 2 degrees of freedom one. There is just one little trick that maps the end effector into the last frame point, the last joint frame, and then you can apply exactly the same procedure. Anyway, we will see next time this in detail. Okay, see you next week.
Thanks, Steve.